Hi everyone, welcome to my presentation entitled Bias Dependent Exciton Stark Shift and Franz-Keldysh Effect in Beta Gallium Oxide Sub-bandgap Photoresponse. I am Mohammad Musinur Rahman Adnan, an EC PhD student at Ohio State University, and my today's talk will show you the observation of exciton peak redshift and Franz-Keldysh effect in beta gallium oxide, and I will present a model that will actually show you how the peak position of this exciton can be used for electric field mapping. And finally, I will be presenting a mechanism for beta gallium oxide photocurrent response that will be explained in terms of peak amplitude. So recently from our group, we have published a paper in APL that showed that Franz-Keldysh effect is unable to explain the gallium nitride photocurrent spectra. So what's Franz-Keldysh effect? It's an effect where if we apply an electric field on a material, then this material can absorb photons with an energy that is less than the band gap energy. So if we apply this model to gallium nitride spectra, we could not really match it well with good R squared value, and also this model failed to explain the built-in voltage that had been measured using CV characterization or capacitance voltage characterization. So we had to use Stark modified exciton Franz-Keldysh effect for gallium nitride. So what is exciton? An exciton is an electron hole pair that is interacting with each other using Coulomb interaction. As a result, they are situated inside the band gap in Coulomb potentials. If we apply an electric field so that Franz-Keldysh effect could be seen, then these excitons could absorb photons with an energy that is smaller than the band gap energy. This effect could be further helped by the Stark effect. So the Stark effect is actually by applying an electric field, these electron and hole pair can be further moved into the Coulomb potential, and as a result, they can actually absorb a photon energy that is much less than the band gap energy. So this Stark modified exciton Franz-Keldysh effect was used to model the experimental data, and the data was fitted very well. And also the built-in potential that came out from this model was actually similar to the capacitance voltage measurement. So this model actually succeeded instead of the Franz-Keldysh model. Due to the success of XFK model in gallium nitride, we wanted to see if it can be used for beta gallium oxide as well. You can see for gallium nitride, the exciton peak below band gap is much smaller compared to the exciton peak that is shown for gallium oxide. This happens because the binding energy of gallium nitride is much smaller than the binding energy of gallium oxide. So we can hope that in gallium oxide, we can see the XFK effect more prominently. So this is our experimental setup. We have a xenon lamp as the source, which produces light that goes through slits, mirrors, and diffraction grating to produce a single wavelength light source. This single wavelength continuous light is then changed into a pulsed light using a chopper mechanism. This pulsed light falls onto the photoelectronic device and produces a alternating photocurrent that is read out and displayed by the lock-in amplifier. So this device is actually a Schottky diode with a Schottky junction at the top and a 1 micron UID gallium oxide layer just below it. You can see from band diagram that almost all of the field is dropping inside that 1 micron of UID layer. So we measured the data and we see two things. The first thing is the peak is red shifting, and also the peak amplitude is variably increasing. So we now model our results. We divide the gallium oxide layer into three parts: the depletion region, the non-depleted absorption region, and the non-depleted non-absorption region. We say that light as a flux is introduced into the device, and it is reducing as it goes through these layers. And these are the fluxes that we get out of each layer. If the final output flux is subtracted from the input flux of the gallium oxide layer, we get the gallium oxide absorption amount. And if we say that there is 100% conversion efficiency, then we get a photocurrent equation. Then we assume two rules. The first one is the reflectivity is very low from the top metal, and the absorption in the non-depleted region is very small. As a result, we get a normalized photocurrent equation, which depends only on the average absorption in depletion region and the depletion y. So we actually model the spectra and plot it with increasing field with a constant bias model, where we keep the bias constant and change the field and depletion y to see what happens. So we can see there is a peak redshift with increasing field. We can also change the bias by changing the depletion width but keeping the field maximum constant, and thus get different field profiles. We can see that for different biases, the peak position comes out to be same for a given field maximum. So we know that the peak position is only a function of field maximum. So we can actually create a transfer function that produces field maximum as a function of peak position. From our experimental measurement, we know peak position is a function of bias. So by putting these two transfer functions together, we can actually see the field maximum to be a resultant of applied bias. And with applied bias, this field maximum is actually increasing. An interesting thing to note here is that the field maximum is saturated at about above 30 volt. And it is saturated near the breakdown region, which is 6 megavolt per centimeter for gallium oxide. As the device will break down at about 50 volts, so we can say that this saturation is actually validating our model because we are near the breakdown limit when the device actually breaks down. Now we will be talking about the peak amplitude increase. So the peak amplitude is a function of applied bias from our measurements, and we already have seen that the field maximum is related with bias. So we can actually plot the peak amplitude as a function of field maximum, and we can see that the peak amplitude suddenly shoots up at about 4.5 megavolt per centimeter. This kind of shooting up of peak amplitude has been previously seen in literature, where this effect has been explained as a reduction of Schottky barrier by self-trapping of holes. But this literature data is actually way above the theoretical limit of photocurrent response. But our observed data is much lower than the theoretical limit of photocurrent response. So we cannot use the model that had been shown in literature. Instead, we have to invoke internal quantum efficiency. We have already said that our conversion efficiency was 100%, but maybe that's not true. That can be seen from our rate-limited photocurrent generation process. At first, in gallium oxide, there was only a free exciton. This free exciton could recombine, it could self-trap, or it could dissociate. If it dissociated, then it could create free electron and hole. Those could recombine or drift. But if it could self-trap, then the self-trapped exciton could recombine, or it could dissociate into self-trapped hole and free electron. The self-trapped hole could further dissociate and become a free hole, or it could recombine. Similarly, the electron could drift or recombine. And finally, the free hole that was created from self-trapped hole, that could also drift or recombine. The recombination processes are loss paths, so they are ignored. The electron paths are also ignored because they are neutralized by the hole paths. So finally, there are only two effective paths for photocurrent generation. And in the lower table, we see the time scales for different parameters in the paths from literature. We see that the free exciton to self-trapped exciton conversion time has a ceiling of 0.5 picosecond, but not a specific value. So we model our time scales using the rate equations from Choudhury et al. And we plot them. We see that the dissociation time of self-trapped hole, that is the rate limiter because it's too high compared to all other time scales. And if we use these values to calculate the efficiencies of the two paths, the free exciton dissociation path and the self-trapped exciton to self-trapped hole path, using a variable that is free exciton to self-trapped exciton conversion time, which can have a value of 0.15 femtosecond and the hole mass as 20 m0. Remember, hole mass is not known because the valence band is very flat in gallium oxide. We actually see a behavior which is controlled by the self-trapped hole dissociation mechanism. And the efficiency is actually shooting up at about 4.5 megavolt per centimeter. So ultimately, adding these two path efficiencies and multiplying with normalized results, we actually get a field-dependent photocurrent spectra for a constant bias that has a amplitude variation, which can be matched with our experimental data by normalizing them with respect to the maximum peak amplitude. So in this work, we have shown the Stark modified XFK model for gallium oxide Schottky diode. We have actually shown that the exciton peak can be used as a peak position, can be used as a sensor for the field maximum. We have validated our results with showing that the saturation happens at about the breakdown region. And finally, we have estimated previously unknown hole mass and exciton self-trapping time by describing a photocurrent generation mechanism and matching it with experimental data. So thank you everyone for listening to my talk. We thank Professor Rajan and his students for helping us with engineering the device. If you have any question, please ask.